Bismillahirrahmanirrahim. Good evening, everybody. In this lecture, we are going to continue our discussion about differentiation, and actually, we are going to finish this part in this lecture, inshallah. The remaining point about differentiation is to consider some application of the differentiation process, and actually, we have started the first one, which is studying the behavior of functions, and also consider the problem of optimization, by which I mean finding the maximum value and the minimum value of some given function. This is the first application, and we have started it and are going to finish it in this lecture, inshallah. As the next application, which will be covered also in this lecture, inshallah, is L'Hopital rule, which is a simple yet important rule to compute the limit of a function using the derivatives. And let's make a quick refreshment about the first point, function behavior and optimization. We started with the problem of determining when a function is increasing and when a function is decreasing, and we arrived at this general test to solve this problem, and we arrived at the conclusion that if f prime of x is positive, this implies that the function is increasing, while if f prime is negative, this implies that the function is decreasing. After that, we turn our attention to the problem of finding maximum and the minimum value, and also we arrived also at this general conclusion. We start by finding the critical points and then apply what's called the first derivative test. The critical points is the points that satisfy any of these two conditions. Either the first derivative equals 0 or the first derivative does not exist. So we start by finding these critical points. After that, we check whether these critical points represent a local minimum or a local maximum or neither of them. If there is a change in the sign of f prime from positive to negative, this implies that we have a local maximum. If there is a change from negative to positive, this implies local minimum, and if there is no change, this implies that there is no local extrema, no maximum, no minimum at this point. Now we turn our attention to a related problem, which is finding the absolute maximum and the absolute minimum. We consider till now what's called local maximum and local minimum. By local maximum, we mean a value of this function which is bigger than all values close to this value, and the same thing for the local minimum. But now we want to find the global maximum and the global minimum, which is usually called absolute maximum and the absolute minimum. By absolute maximum, we mean the maximum value that the function takes over some given interval, and also by absolute minimum, we mean the minimum value the function take over some given period. For example, in this graph, we can say that this value is a local maximum, and also this value is a local maximum. But if we compare these two values, we find this value is bigger. So about the shown interval, this is the absolute maximum. And similarly, the absolute minimum of this function over this interval is this point. So by absolute maximum of some function f, we mean a value of this function, for example f of c, which is greater than or equal to the value taken by this function at any point in some given interval. And also by absolute minimum, we mean a value of this function at some point c, which is smaller than or equal to any value taken by this function over some interval. And actually, absolute maximum or absolute minimum may occur at a critical point. That's to say, it is a point that contains local extrema, or also will be at the end points, because we consider in general a closed interval. So the absolute minimum or absolute maximum may be also at the end points, as in this case here the absolute minimum is at this end point. So the absolute maximum or absolute minimum may be at a critical point. It is a local maximum and local minimum, but for example, it is a local maximum which is greater than any other local maximum, so it is named the absolute maximum, or maybe at the endpoints, one of the endpoints, because at this endpoint, for example, the value taken by the function is greater than any other value taken by the function over this interval. So the value at this endpoint is called the absolute maximum of this function. How to test the absolute maximum and the absolute minimum? How to find the point at which the function takes its absolute maximum or absolute minimum value? If you consider a function which is a continuous function, and we study this function over some closed interval from a up to b, we are sure that this continuous function has an absolute maximum and absolute minimum, because this function is continuous. So it is a continuous function, so it must have a value which is the maximum value and another value which is a minimum value. If we imagine any continuous function of any shape, over some closed interval, so it should have an absolute maximum. In this case, this is absolute maximum. This is the absolute maximum over this interval, and in this case, this is the absolute minimum over this interval. So if the function is continuous over some closed interval, it must have an absolute maximum and also an absolute minimum. Now, how to find this absolute maximum and absolute minimum is very simple. We start by finding the critical point, and also consider the value of the function at this critical point, and also find the value of the function at the endpoints of this interval. So we find the value of the function at two classes of points. We find the value of the function at the critical points, and also find the value of the function at the two endpoints, and then make a comparison. So if the comparison gives that the maximum value, for example, at one of the critical points, so this is the absolute maximum. If the comparison is for the endpoint, then this endpoint gives the absolute maximum of the function, and similar thing for the absolute minimum. So to summarize, we can say that we have two sets of points, and we evaluate the value of the function at the points in these two sets, and then take the maximum of them to be the absolute maximum and take the minimum of them to be absolute minimum. Let's consider an example. We want to find the absolute extrema, by which we mean absolute maximum and also absolute minimum, for this function over the interval from 1 up to 4. So in this case, we have to find first the critical points of this function and evaluate the function at these critical points, and then also find the value of the function at x equal 1 and at x equal 4, and then make a comparison between all these values. The maximum will be absolute maximum, the minimum will be the absolute minimum. To find the critical point, the critical points, as we said before, are the points at which f prime equals 0 or f prime is not defined. In this case, this is f prime. It is defined for all x. So the unique source of critical point is when f prime equals 0. In this case, f prime equals 0 at x equal 2 or x equal -2. So we have two critical points. But take care, we cannot assume that x equal -2 is a critical point, because we are considering the function over this interval from 1 up to 4, and -2 is outside this interval. So we have a single critical point, which is x equal 2. So now we have to evaluate the function at this point, and also evaluate the function at 1, and finally at 4, and then compare these three values. These are three values. At 2, which is a unique critical point, at 1 and 4 also, which are the endpoints. Simple comparison implies that this is the maximum value of the function. So this is the absolute maximum. And this is the minimum value of the function. This is the absolute minimum. And the graph of the function coincide with this conclusion. This is the absolute minimum at x equal 2. And this is the absolute maximum at x equal 4. So the absolute minimum is -0.5, and the absolute maximum is 10⁻³. Now there is a related concept to the problem of maximum and minimum, which is the concept of concavity. We know that if we have a maximum value, so we expect the graph to be of a form like this. This is the absolute sorry, we are talking about total maximum. To have a local maximum, we expect the graph to be of this form. We have the function increase up to submaximum and then decreases. So the curve is shaped as this. And in the local minimum, we expect a shape of this form. The function is decreasing until a local minimum and then increasing. So in this case, we can say that the graph is concave down. And in this case, we can say that the graph is concave up. So the concept of concavity is very related to maximum and minimum. So let's start by defining what's meant by concavity and how to test concavity and determine whether the graph is concave down like this or concave up like this. And then relate the concept of concavity to finding maximum and the minimum value of some given function. Let's start by the meaning of concavity and then the test of concavity. A function is concave up like this if the graph is bends upwards as this graph, or for example a more clear graph like this is bends upward. And in this case, we notice that the slope of the tangent line increases. This is the slope of tangent line, some positive number. This is another tangent line with x increases. The slope of this line is greater than the slope of this tangent line. And this is another tangent line with x increases. The slope of this line is greater than these two slopes. So in general, for a function to be concave up, the slope of the tangent line should increase. And also we notice that in concave up function or concave up parts of a function, the graph should lie above the tangent line. The graph should lie above the tangent line. The reverse of this consideration exists in concave, this is concave down. This is written incorrectly, this is concave down. This should be concave down. A function is concave down when we have the reversed points. The graph is bent downwards like this or like this, for example. And the slope of the tangent line decreases. This is the slope of the tangent line, some positive number. The slope here is a smaller positive number and this slope is almost zero. So the slope of the tangent line decreases. And also in the case of concave down, the graph lies below the tangent line. The tangent line are above the graph. So this is the meaning of concavity. How to test concavity? Actually, the test of concavity is related to this point. The slope of the tangent line, increases. And we notice that in the first application of derivative, we find a way to test increases and decreases of some function, to test when the function increases and when the function decreases. But in this case, the function is the slope itself, the slope of the function. So the slope is the first derivative. So we want to test when the first derivative increases and when the first derivative decreases. So we have to differentiate the first derivative to test when it is an increasing function and when it is a decreasing function. So we have to differentiate the first derivative, so we have to find the second derivative. If the second derivative is positive, this means that the slope increases, and if this second derivative is negative, this means the slope decreases. This is the basic idea to test concavity. Let's consider some simple example. The graph e to the power negative x is a concave up graph. If you draw some tangent line, you find that the slope of the tangent line increases. The slope of the tangent line decreases. This is a tangent line with negative slope. This another tangent line with a negative slope, but for example, the slope here may be negative 10, for example. The slope here is negative 1, and the slope approaches now 0. So the slope of the tangent line increases. So it is a concave up, and as you see, the graph is above the tangent line. This graph is concave down. Here the slope is some positive number, the slope then is 0, then the slope of some negative number. So the slope decreases, and the graph is always below the tangent line. The tangent line are above the graph always. Now, some graphs contain parts where the graph is concave down and some other parts when the function is concave up. For example, the graph of x bar 3. In this part, the graph is concave down. If you draw any tangent line, you find the graph is below the tangent line, so it is a concave down graph. But in this case, the tangent line can be written in this form or drawn in this form. So in this case, the graph will be above the tangent line. So the graph here is concave up. So the behavior of the function changes from concave down to concave up. The point at which we have this change in the function behavior in the concavity of the function is called the inflection point. So the inflection point is the point at which the behavior or concavity of the function is changing from down to up or from up to down. Now we want to relate the concept of concavity to find the maximum and the minimum. As we said before, in order to test concavity, we depend on the second derivative, because the second derivative determine when the first derivative increases and when the first derivative decreases. So if the second derivative is positive, this means the slope of the tangent line increases and then the function is concave up. But if the second derivative is negative, this means that the slope of the tangent line decreases, and this implies that the function is concave down. So if we apply this sample test to this function, we start by finding the first and second derivative. This is the second derivative. Now we check when this second derivative is positive and when this second derivative is negative. It is very simple. This second derivative equals 0 at single point, which is equal x equal 1. If we substitute with any value which is smaller than 1, we find that f double dash is negative. And if we substitute with any value which is greater than 1, we find that this second derivative is positive. So in this case, the second derivative is negative. This implies the function is concave down in this interval. And in this part, the second derivative is positive, and this implies that the function is concave up. And if you draw a graph of this function, this coincides with this conclusion. Here the function is concave down, and here the function is concave up. Now, the relation between concavity and maximum and the minimum. The concavity now is used to test whether some critical point is a local maximum or a local minimum. The concavity is used as some critical point to determine whether this critical point is a local minimum or it is a local maximum. And this is usually called the second derivative test for local extrema. So if a critical point, as this one, if we have some critical point and the function is concave up, similar to this function, the function is concave up at this critical point, then this means that we have a local minimum. And if we have some critical point and in this point the function is concave down, so this implies that we have a local maximum. So the local maximum, the concavity is used to determine whether a critical point represents a local maximum or a local minimum. This is called second derivative test, and we can summarize it as follows. We start by finding all critical points. As before, a critical point is a point at which the first derivative equals 0 or the first derivative does not exist. And then instead of we did in the first derivative test by checking the change in the sign of this first derivative first derivative, we depend on the second derivative. We depend on the second derivative to determine which of these critical points represent a local maximum and which represents a local minimum. So we find the second derivative and check each sign only, not the change in sign, but only its sign. If this sign is negative, like this case, if the second derivative is negative, then we have a local maximum because the function is concave up. If the second derivative is positive, then we have a local minimum because the function is concave up. Again, if the second derivative is negative, like this one, then we have a local maximum because the function is concave down. If the second derivative is positive, as in this case, then we have a local minimum because the function is concave up. We have a very important case when f double dash equals 0. If f double dash equals 0, then we cannot get a conclusion from the second derivative. We have to return back to the first derivative. If the second derivative equals 0, we cannot say that this is the local maximum or local minimum, or perhaps don't have any local extrema at this point. So we have to return back to first derivative test and check the change in the sign of f dash. So this test succeeds only if f double dash at some critical point is positive or negative, but it fails when the second derivative equal 0. Let's take an example. If we want to find the local extrema at this point using the second derivative test. So we start by finding the first derivative to find the critical point from it. This is the first derivative. If we set first derivative equals 0, we get two critical points, 3 and negative 3. And I think it is clear that this first derivative is defined for all x, so we don't have values at which the second derivative does not exist. So the critical points only are 2 points, 3 and negative 3. Now we want to determine which of these points represent a local maximum and which represent a local minimum. We can depend on the first derivative test and check the change in the first derivative as these 2 points, but we want to find it using the second derivative test. So now we go to the second derivative and substitute with 3 and with negative 3 and check the sign of second derivative as these 2 points. At x equal 3, the second derivative is negative. This implies a local maximum. When the second derivative is negative, this implies a local maximum. And at x equal negative 3, the second derivative is positive, and this implies a local minimum. When the second derivative is positive, we have a local minimum. And the graph of this function can confirm this conclusion. Let's take another example. We want to find the local extrema of these points. We start by finding the first derivative and put it equal to 0, and then from this equality, from this equation, we get the critical points. We have two critical points, x equal 0 and x equal 1. Now we want to determine which of these points represent a local maximum and which represent a local minimum. We want to depend on the second derivative test. So we substitute with x equal 0 and check the sign of y double dash, and also with x equal 1. If you put x equal 0, we find that y double dash equals 0, and in this case the test is inclusive. The test failed. The test cannot determine whether this point represents a local maximum or a local minimum. So we have to return back to the first derivative test and check the change in the sign of the first derivative. But if you put x equal 1 in the second derivative, the value is positive. The result in this case will be a positive number. A positive number implies a local minimum. So in this case, the test gives a conclusion, and the point x equal 1 represents a local minimum. But now for x equal 0, we don't have a conclusion. So we have to return back to the first derivative test and check the change in the sign of y double dash about x equal 0. It is very simple. If you put value smaller than 0 and greater than 0, but it should be close to 0. We cannot, for example, put a value which is greater than 1. We have to check the change in the sign of f dash about 0. A very close value to 0 before, and another value which is very close to 0 but greater than 0. We will find that this value will be negative, and also this value will be negative. So there is no change in the sign of f dash about this point. So this point does not represent any extreme. So we have a single extreme point at x equal 1, which is a local minimum. Let's conclude this application of a derivative by an example. A practical example, a simple practical example. As we said in the introduction, the finding maximum and the minimum is very important for any engineer, because always the main target of any engineering design is to maximize the gain from this design and minimize the cost of this design. So the problem of finding maximum and the minimum, or setting or finding the best setting to get the maximum gain and pay the minimum cost is very important to engineer. So finding the maximum and the value and minimum is very important. Let's consider this example. Assuming that we have an object, its weight equal W of this object is dragged along some horizontal plane. And the force is acting along a rope attached to this object. We assume that this rope make an angle theta with the blade. So we can imagine that this is the ground and we have this object. This object is dragged with some force F, and this force make an angle theta with the ground. Make an angle theta with the ground. Based on this setting, we can say, or we can conclude that the force is given by this expression. The force depends on the weight of this object. It depends on the angle theta, and also it depends on mu. Mu is the coefficient of friction of this surface. Friction coefficient of this surface. So we want to find the minimum value of F, assuming that we can exchange theta. So we can imagine that theta is the variable, theta is x now, this is the variable, and we want to adjust theta in order to make this force minimum. And actually we want to prove that this force is minimized when tan theta equal mu. In other words, when we set theta equal tan inverse mu. This is the value, this is the angle that make this force minimum value. How to prove? Very simple. We want to find the minimum value of this function. This is the function in theta. W is constant and also mu is constant. The single changing quantity is theta. So this is the variable. So we can say that F is a function of theta. And we want to find the minimum value of this function and make a proof that this minimum exists when when tan theta equal mu. Proceed as before for any numerical example or classical example. We find first the critical point at which f dash equals 0 or undefined, and then use either the first derivative test or second derivative test to determine which of these critical points represent a minimum and which represent the maximum, and then consider only the minimum value. So we start by finding the first derivative. This is the first derivative. We apply the quotient rule, and this is the first derivative. Now this first derivative will be both equal to 0, and then this equation can be solved very easily by equating the numerator to 0. From this equality, we conclude that tan theta equal mu, which is required. So tan theta equal mu is a critical point. But we have to prove that this critical point represents a minimum point. We arrive at the conclusion that there is a critical point at tan theta equal mu. Tan theta equal mu. But we want to confirm that this critical point represents a minimum value of the function f. So we depend, for example, on the second derivative test. We find the second derivative test, and we can prove that second derivative test is positive at this point. We can make a proof that the second derivative test is positive at this point, which implies that this point represents a local minimum because the second derivative is a positive number. And actually, to get some more understanding of the problem, if you graph the function f, assuming some numerical values for the constant w and mu, assume for example the weight equal 10 and the coefficient of friction equal 1, the graph of the function as a function of theta now, the graph of the force f of theta as a function of theta looks like this graph. And you can see in this graph that when you increase theta, the force decreases, but up to some minimum. And then after this minimum value, if you increase theta, you return back to increasing force. So this is the required point. This is the required point at which the force is minimized. This is the always objective of optimization. We want to find the best setting of the parameter. Here, the best setting of the angle theta, because other setting may lead to greater force. We want to find theta that minimize the required force. That's all about function behavior, the first application of differentiation. And in the next part of the section, we are going to talk about L'Hopital rule, inshallah. Thank you.